Everyone, I am Prabhakar Singh. Today, I'm going to take you inside how a spam detection is handled at truly massive scale. We are talking about billions of users, millions of decisions every second, and everything has to happen in real time. Now, when we talk about a spam, it's not just annoying messages. We're talking about fraud, phishing, scams, harmful content, etc. Things that directly affects users' trust and platform integrity. And here is the hard part. At this scale, even a tiny error, say a tenth of a percent, means millions of people are impacted. And that's why we need MLOps that is not just clever, but resilient, privacy preserving, and battle tested. So let me walk you through how we are going to explore this challenge today. So here is the roadmap. We'll start by looking at unique challenges of working at billion user scale. Then I will show you end-to-end MLOps architecture, how large-scale systems design pipelines to keep up with the constant change. We'll also dive into data strategies because what data you choose, either to label and or to train, is absolutely critical. Then we will look at the production side, like scaling, monitoring, and incident response. Finally, we will end by looking ahead what spam looks like in the future and the technologies we will need to stay ahead of it. So think of this talk as a blueprint, not just theory, but patterns you can adapt to your own systems. So let's start at the beginning, the sheer challenge of operating at scale. Every day, billions of pieces of content move across platform. At peak load, large-scale systems are making millions of evaluations per second. And for user-facing decisions like blocking a comment or flagging a post, response must be under 100 milliseconds. Now think about the consequences of error at this scale. A 0.1% false positive rate does not sound terrible in theory, but in practice, that could mean millions of legitimate users waking up to find their posts are blocked or comments are deleted. And on the other side, false negative means spam or scams getting through to the millions of people and harming them. The constraints are equally tough. Large-scale systems are detecting across text, images, videos, even behavioral patterns. They have to support hundreds of languages as well. Like they have to constantly adapt because attackers change tactics every day. And all of things must comply with strict privacy laws like GDPR and CCPA. It's like playing chess with millions of opponents and they all change their strategies overnight. So meeting challenges like this requires more than just good models. It requires end-to-end MLOps architecture, and that is we are going to talk about next. Here is what that looks like. First, ingest data from multiple sources, which includes real-time streams and batch histories. Then comes feature engineering, where they extract both instant signals like device fingerprinting and long-term signals like account history. Models are retrained continuously, often daily, but training is not enough. You have to validate rigorously against golden data sets, fairness checks, and adversarial examples. And when a deployment happens, they don't just flip a switch. We have to use a shadow deployments where new models can run in parallel silently for days, weeks, or even months. And then canary rollouts are there, which gradually shifting traffic with instant rollback if needed. This is not just a pipeline, it's a living system. It adapts, learns, and recovers without stopping. But what makes these models powerful is not this, but the features we built from the multi-modal data. So let's discuss about this multi-modal feature engineering. Spam today does not come in just one form. Attackers use text, images, videos, and even behavioral manipulation. For text, Large-scale systems use transformer embeddings like BERT, engrams, entity recognition, sentiment, intent classification, and etc. For image and video, you can rely on CNNs like EfficientNet and ResNet. OCR are very common for memes and frame sequence analysis. But content is only half the story. Behavior is often the giveaway. Things like account A's posting frequency, engagement metrics, or unusual device fingerprints can just be as revealing as others. Finally, context matters the most. For example, a post at 2 a.m. from new device linked to trending spam topics tells a different story than the same post from a long-standing account. When you put all these signals together, you catch patterns no single dimension can reveal. Now, let's look at how we bring those signals together in the model itself. Something we call a model architecture ensemble approach. So where large-scale systems don't rely on one big model. Instead, they use a hierarchical ensemble. First, do a fast pre-filters where lightweight models that can process use volume quickly. They're designed for high recall, catching anything even slightly suspicious. Now we bring into a specialist model here, like deeper, which has deeper domain-specific networks for text, images, videos, behavior. And then comes the multi-modal fusion where we're combining the signals using cross-attention. This is where we find hidden correlations. Like when the text looks fine, but paired with image features, it becomes clearly a spam or a harm. Finally, a meta learner integrates everything, weighing outputs based on historical reliability. The result is speed when we need it and depth when it matters. It's the difference between quickly scanning luggage at an airport versus pulling aside a suspicious bag for deeper inspection. And to serve this model in production, we need a specialized infrastructure. So let's talk about distributed serving architecture. Serving at a scale is a systems challenge as much as an ML1. Large-scale systems use context-aware load balancing to send requests to the right resources. Horizontal auto-scaling helps us handle sudden traffic spikes. A low-latency feature store can ensure models gets what they need without recomputing, and specialized hardware like GPUs and TPUs accelerates inferences. Performance optimization is constant. Model quantization makes networks smaller and faster. Batching lets us process multiple requests together. Prioritization ensures critical cases are not stuck in the queue, and the circuit breaker prevents cascading failures if something goes wrong. All of this will allow to consistently hit 80 millisecond end-to-end latency even under extreme load. 80 milliseconds, this is just a figure. It could be anything, whatever matters to the organization. But even the best infrastructure needs smart data strategies to keep the model learning. So let's talk about smart sampling and learning strategies. Leveling billions of samples is not possible. It's simply not possible. The question is which samples matter most. So large-scale systems use uncertainty sampling, like sending low confidence cases to human review. Diversity sampling makes sure we don't miss underrepresented languages or formats. Adversarial sampling deliberately seeks out the cases where models fail on, making the system even stronger. And time-sensitive sampling ensures we catch new attack vectors as they emerge. Together, these strategies drastically reduce labeling cost while keeping the models robust. One example I can think of is like when attackers started hiding spam in memes, adversarial sampling surfaced these cases early, letting retrain before it spread widely. But not all spam comes from individual. Often it's coordinated campaigns. Let's discuss a little bit about coordinated attack detection. This is where things get interesting. A single post may look normal, but when thousands of accounts act in unison, that's a coordinated attack. Large-scale systems use real-time streaming analysis to spot anomalies in activity patterns. They apply graph neural networks to model user content interaction as dynamic graphs, exposing suspicious clusters. And they deploy countermeasures in real time, like throttling activity, adding frictions with captchas, or flagging suspicious clusters for further review. One case we can discuss here is like 10,000 accounts liking a post in under 1 minute. Individually, nothing stood out. But when viewed as a graph, the coordination will be obvious. Now, while large-scale systems might fight these attacks, they also have to protect user privacy. Everything I've described so far has to be done under strict privacy laws like GDPR and CCPA. Large-scale systems use federated learning to train across decentralized data without centralizing raw content. Differential privacy ensures individuals can't be re-identified. The systems also employ advanced cryptographic techniques like homomorphic encryption for secure inferences, multi-party computation for trust distribution, and zero-knowledge proofs for compliance without exposing raw data. The key point being here, privacy and performance are not opposites. With the right techniques, you can have both. Now, let's look at how to keep these models fresh and reliable in production. The training cycle is continuous. The large-scale systems retrains models daily on fresh data using Bayesian optimization for hyperparameters, then evaluate against golden datasets, fairness slices, and adversarial examples. New models run in shadow deployment first, silently for coding real traffic without affecting users. Once stable, they move into progressive rollout, which means canary test, gradual traffic shifts, automated metric analysis, and instant rollback if something slips. This rhythm ensures the model keeps pace with evolving spam tactics without ever destabilizing the system. But the deployment is only half the story. Monitoring keeps everything healthy. Usually, large-scale systems monitor at 4 levels: model performance, which basically is precision, recall, and drift detection. And system performance is another, which has request latency, queue depth, and resource utilization. Data drift is third one, which includes metrics like feature distributions, schema validations, statistical tests. And business impact, of course, like user engagement metrics, false positive appeals, and of platform health. The idea is to catch problems before users do. When it's a model drifting, like whether it's a model drifting or a sudden traffic spike, we want to detect early and respond fast. And when issues do happen, rely on a structured incident response. So let's talk about anomaly detection and incident response here. So we know incidents are inevitable. Resilience comes from how you respond. Large-scale systems use automated anomaly detection, which involves outlier detection, multivariate analysis, and baseline comparisons. If something is off, the systems follow structured playbooks: severity-based escalation, automated rollbacks, shadow mode for investigations, and configurable safety thresholds. And after every major incident, run post-mortem, not just to fix, but to learn and strengthen the system. This structured discipline turns outages into opportunities for resilience. Now, let's look forward. What's next in this arms race? So the arms race is not slowing down. First, synthetic content. Let's talk about that. Attackers are already experimenting with AI-generated spam, deep fakes, synthetic text that slips past filters. Second, cross-platform coordination is another thing where spam campaigns don't stay confined. They spread across apps and platforms. Collaboration while preserving privacy will be the key here. Third, let's talk about adversarial robustness. We must strengthen defenses against intentional manipulation of models. Finally, explainable AI. Enforcement actions must be transparent, both for users and regulators. We need models that not only predict, but also explain why it took certain action. The future will demand even faster adaptation. This is not a one-time problem, but a continuous race. So let's wrap this up with the key takeaways. Here are 4 key principles I want you to remember. Spam detection must be multi-modal, meaning you have to take care of text, images, videos, and behavior together. MLOps at billion user scale requires a specialized architecture is something we have to be aware of. Privacy and performance can coexist with the right techniques. That's very important. Continuous adaptation is non-negotiable. You must know this is an evolving arms race. If you keep these principles in mind, you'll be better prepared to design systems that don't just work in research, but that scales in the real world. And with that, let me thank you. So thank you for listening. I hope this gave you a clear look into what it takes to build robust, scalable, privacy-preserving MLOps system for spam detection at global scale. This fight against spam never ends, but with the right architecture, we can stay ahead. Thank you.